Yeah, thank you very much, Yunsi. Indeed, we have had a look at how aircraft wake vortices can affect airport wind measurements, and this work was done by myself, Lena Nölk, and also Raphael Monche. So I want to start this presentation with a brief example scenario. So imagine you're the pilot of a Boeing 777, and you have just lined up on runway 34 at Zurich Airport. And shortly afterwards, you get your takeoff clearance, which, as usual, also includes a wind report. And this report states the wind at 150 degrees and 5 knots, with gusts of up to 10 knots. You suddenly realize that this wind differs a lot from the one that you expected, and also from the one that you used for your takeoff performance calculations. You also realize that you will not be able to take off with that reported wind, and you will have to change to a different runway, or even get back to the gate to offload cargo. This is a rather unfortunate situation, but wind is something which you cannot influence, and you were probably just really unlucky that the conditions changed this drastically over that short period of time. But what if the wind conditions that are reported do not reflect the actual wind, but are instead heavily affected by the wake vortices of another departing aircraft? There was a suspicion that exactly such cases were happening for departures on Zurich's runway 34. And the wind sensor that's used for the takeoff clearances on 34 is actually located beyond the runway end, around 200 meters to the right of its center line. And the suspicion was that at times aircraft departing runway 34 can generate wakes, which then descend down and move to the right, getting close to that wind sensor and thereby affecting its readings. This sounded like a really interesting and relevant case to us, which is why we had a closer look at it. So in a first step, we had to try and identify such occurrences amongst takeoffs from runway 34. And we did this using a two-step identification method, the first of which was a visual classification, followed by a wake model verification. We analyzed the period from March 2022 to May 2023. And for that period, we obtained the wind measurements from that concerned sensor. And we then also fetched all available ADS-B trajectories corresponding to takeoffs from runway 34, of course, from OpenSky Network's historical database. And this resulted in a total of 2,028 takeoff trajectories. Based on this data, we then generated one plot, such as the one shown here in the bottom right, which essentially shows us the wind measurements around the time the aircraft passes by this sensor. And we then used these plots. So all three authors went through one such plot for each takeoff, classifying if it looks that this aircraft generated a wake that hit the station or not. So here, this plot on the bottom right is a prime example of what such a hit looks like. So we can see that shortly after the aircraft passed by the sensor, we have clear fluctuations in the wind speed, and at the same time also a significant change in wind direction. And both values then go back to the previously observed values after just 2 to 3 minutes. So this then resulted in 3 classifications for each of the takeoffs, and we then applied a majority rule to get just 1 classification per takeoff. To reduce the probability of false positives in our classification, we then applied the second step of our method, but this time only to the takeoffs that were previously classified as hit through the visual classification step. And we thereby applied DLR's P2P wake vortex model to kind of simulate the propagation of the generated vortices along a 2-dimensional plane that's perpendicular to the runway center line and intersecting the sensor. So essentially what we see the situation in the bottom left picture. As I mentioned, we did that for all the takeoffs that were previously positively classified. Of course, using input parameters to the model that correspond to that specific takeoff. What we get out of that model is what we can see in the bottom center. So we get the evolution of the position of both vortex cores along that 2-dimensional plane, along also with their vorticity and all that over time. We then use that additional information to re-evaluate each of the previously identified cases And they only kept their positive classification if also the wake model output seemed to confirm that assumption. This then resulted in our final classification, which we used for all the following steps. So we first used the resulting data to do some exploratory analysis to kind of learn more about these occurrences and also potential influencing factors. And out of these 2,028 takeoffs, we have identified 102, so around 5%, that seem to have generated wakes that actually hit this sensor. We assumed that both the wind conditions as well as the aircraft type are relevant factors that influence on whether such a hit occurs or not, and therefore we had a closer look at that as well. So the polar plot here on the right side shows us the wind conditions for each of the analyzed takeoffs, distinguishing between takeoffs that caused hits in orange and those that did not in blue. And we can also see the runway heading of runway 34 with that red line. We can clearly see that basically all cases where a hit occurred correspond to takeoffs that took off under conditions that represent the wind coming from the left side of the runway, which is to some extent to be expected since the wind sensor is located slightly to the right. And we can also see a cluster of increased density of hits for conditions between 180 and 270 degrees and wind speeds of below 7 knots. A similarly interesting picture could be seen when looking at the aircraft types. So this bar plot shows the distribution of aircraft types in overall takeoffs, with the orange part of the bar showing the takeoffs that caused hits. And we can see that almost all the hits are caused by Airbus A340s and Boeing 777s, with just one additional hit being attributed to an Ilyushin IL-76, which is here contained in the other heavy category. It's maybe also worth mentioning that all the aircraft types that caused hits are of the heavy wake turbulence category. So this initial analysis already seemed to indicate that indeed both the wind conditions as well as the aircraft type seem to have an influence on whether hits occur or not. Nevertheless, we then also fitted a generalized additive model to a subset of this data. However, this subset only included takeoffs of aircraft types that actually caused hits, and we thereby excluded the IL-76 since there was really just one takeoff in the entire data set, and it can be considered an outlier at Zurich Airport. The model essentially confirmed our initial assumptions, and it showed that all three parameters, so the wind speed, wind direction, and aircraft type, are relevant for the probability of a hit occurring. And it also allowed us to determine the scenario with the highest probability for such a hit to occur. And that corresponds to an Airbus A340 taking off under wind conditions corresponding to a direction of around 210 degrees and 4 knots. So we've established that indeed these hits seem to be occurring for around 5% of the takeoffs. And we've also established that apparently both the wind conditions and the aircraft type have an influence on whether they occur or not. For the operational relevance, it's also important to have a look at how significantly they affect the wind measurements. And we'll best do this by looking at a specific example. So here we can see the wind measurements for a 35-minute period on May 14th, 2023. And during this period, we had favorable wind conditions for hits to occur, so a wind speed of around 3 knots and wind direction of around 200 degrees. And during these 35 minutes, we had 3 takeoffs, all of which are of an aircraft type that is prone to generate hits. The top 2 rows, we see the wind speed, wind direction, and just to specify, the third row shows us the tailwind component for this runway 34, the resulting tailwind component. It's also worth pointing out what the air traffic controllers in the tower are actually displayed. So they get an information about the current prevailing wind conditions, which is based on a 2-minute moving average of these measured parameters. So that corresponds to the red line that's in the top 2 plots. And they are also displayed information about the current gusts and these are computed based on the peak values of the wind speed that are observed within the last 2 minutes. So therefore, for the wind speed, it's important to have a look at the measured values in blue, as well as the 2-minute moving average, whereas for the wind direction, it's mainly the 2-minute average in red that's relevant. So before the first takeoff, we have really stable wind conditions of around 3 knots and 200 degrees, as I already mentioned. And this results in a tailwind component for runway 34 of around 2 knots. At around 9:10 in the evening, we then have 2 takeoffs within short succession, both of aircraft type A340. And we can see that both takeoffs cause actually peaks in the measured wind speeds of around 10 knots. And they have a combined effect on the 2-minute moving average, lifting it to around 5 knots, which is sustained for about 3 to 4 minutes. In the wind direction, they change it to around 180, maybe even 170 degrees in peak, which is also sustained for the same period of time. This has a combined effect on the tailwind component, lifting it to about 4 knots. The third takeoff of a Boeing 777 has a very similar effect on the wind speed, also causing peaks of 10 knots and lifting the moving average to about 5 knots. However, it has a slightly more pronounced effect on the wind direction, changing it to about 150 degrees. And this results also in a slightly more pronounced effect on the tailwind component, lifting it to about 5 knots, which is sustained for about 1.5 minutes. So we've seen that apparently these effects seem to be significant, but it's still somewhat difficult to judge how significant that actually is. That is why we used actually the third takeoff from the previous slide to perform calculations of the maximum allowed takeoff weight for a Boeing 777 using the baseline wind and the ones during the wake effect. So if we use the baseline wind before the takeoff, which is a wind of 200 degrees and 2 knots, and use Boeing's onboard performance tool to calculate the maximum allowed takeoff weight, we get a maximum allowed weight of around 347 tons. If we redo the same, but use the winds during the wake effect, but for now ignore the gusts, so we just use the 150 degrees and 5 knots, we get a maximum allowed takeoff weight of 342 tons around, which is already a reduction of 5 tons. It's usually in the discretion of the pilots how much they want to take gusts into account for the calculations. But if we assume that they are fully taken into account, we get a maximum allowed takeoff weight of around 334.5 tons. And this represents a reduction of more than 12 tons compared to the baseline scenario. And here can be said that usually when doing takeoff performance calculations, the margins that they consider for potential wind changes are way below what we get here. So they will never account for these kind of changes in takeoff weight. And it's also worth mentioning that even if a takeoff is still possible under the affected wind conditions, if the pilots are faced with unexpected winds during the takeoff clearance, they are usually forced to do a runway condition change checklist. And this checklist takes about 5 minutes, during which the aircraft is already on the runway and blocking this runway. So therefore, even if a takeoff is still possible under the altered wind condition, it represents a disruption. In the specific case of Zurich Airport, such disruptions can have a potential influence on the overall airport operations, not only the specific runway. And this is due to the specific operation concept and the runway layout. So takeoffs on runway 34 mainly occur when the east approach concept is active. And that's usually in the evening hours just before the night curfew. And under this concept, all landings take place on runway 28, whereas most takeoffs depart from runway 32. And the only aircraft using runway 34 are the ones that are constrained in terms of performance, since it offers an additional 400 meters of runway length and also less restricting obstacles in the departure sector. So therefore, all aircraft using runway 34 are usually rather constrained in terms of performance. Due to the layout of the runways, every takeoff on runway 34 has to be coordinated with both landings on 28 as well as other takeoffs on runway 34, and therefore any disruptions in takeoffs from runway 34 have the potential to cause disruptions for the two other runways as well. Furthermore, in Zurich, there's a series of heavy departures late in the evening, shortly before the night curfew, consisting of mainly Boeing 777s and A340s. And disruptions, delays, or even runway changes for these flights has always the potential to push the departure time beyond the night curfew, which could even lead to flight cancellations. So to conclude, this work confirms the suspicion that indeed wakes of takeoffs from runway 34 can hit the concerned wind sensor located at the end of the runway. We could show that both the aircraft type and the wind conditions are important influencing factors on whether such hits occur or not. We could also show that the wind readings are altered in a way which can cause aircraft an inability to take off. And we've also shown that it can even have an influence on overall airport operations. We are in discussion and have already discussed with the relevant stakeholders at Zurich Airport. And we've discussed multiple mitigation strategies already. These involve the use of a different wind sensor for clearances on runway 34. Also the relocation of the affected wind sensor, or even just raising awareness amongst pilots and controllers so that the situations, if they occur, are handled in the best possible way. It's up to the operational experts to decide which mitigation strategy to use, but we think that the work we performed serves as a basis for a well-informed decision. And we also hope that this work raises the awareness for that specific topic, since there's really no research around about that specific topic, and we think that this problem might not be specific to that situation in Zurich, but that also other airports might suffer from similar issues. Yeah, that would be it. Thank you very much for listening, and I'm open for questions.
All right, thank you, Jan. We are open to questions.
Thank you for your nice presentation. Do you really think this is an operational problem, or is it more a corner case?
More?
A corner case. So for example, when you say, we have this with separation management, we have the pairwise separation.
Mm-hmm.
And they say, okay, if you have this specific pair of aircraft, you will increase your capacity tremendously. And then you check the airport and you didn't find the pair only happening 1% of operation. So this really does not, how do you say, it's not a driver for the operational capacity of the airport.
No, it's not. It's probably not a driver for operational capacity, especially also since runway 34, we've seen over a year, we had only around 2,000 takeoffs. So it's not a capacity issue, but it's more an issue of flights that are delayed. And also that issue I mentioned with the night curfew, since there's a lot of heavy departures in the evening, that they are always already close to that curfew. And if situations like that occur, it might lead to flight cancellations. So it's more an issue for the airlines.
I would see it more like a safety case. You come with that, data, yeah. You can say, okay, if this happens, it could be a safety case, and you only can pay with capacity or with flows, finally. Okay, thank you for this kind of very nice research done.
All right, other questions? Oh, there's online. Xavier, you have to unmute, I think. All right, please go ahead, Dimitri.
Yes, hello, can you hear me?
Yep.
Perfect, thank you. Thanks a lot for the very interesting presentation. I was wondering if the impact of the wake turbulence on the wind sensor is only for the wind reported by the tower over the radio, or if it could also potentially affect the ATIS messages.
The ATIS, I don't know, since I don't really know which sensors they use for that. I think they use a multitude of sensors to compute the ATIS wind reports. But we know that for the meta reports, they use that exact same sensor that's affected. And we have observed a case where the meta report seemed to have been affected by such a case. It was even the example I've shown here. No, it was this one, sorry. The effect of these two A340s, because here we have an effect that lasts for around 4 minutes. And if I remember correctly, for the meta report, they use 10 minutes, so the last 10 minutes before the meta report is generated. And if out of the 10 minutes, 4 minutes are heavily affected, so it could potentially also affect meta reports, I guess.
Okay, thanks a lot. I think the ATIS messages are average over 2 minutes only, and I suppose in that case it means they could be affected. And I would also
definitely. If it was just 2 minutes, then it would definitely have an effect, but it also always depends on what sensors are used, if it's just one or if they merge data from multiple sensors.
Right. Okay, thanks a lot.
Thank you for the question. Any other question from the audience here? Okay, adieu.
Are there cases where the wind has been underestimated?
Yeah, that's a good point. The cases I've shown here, they all looked quite similar, where we had an increase in wind speed and a reduction in the heading. But depending on the wind conditions, the hits can look quite a bit different. We've also observed cases where only one of the two parameters was affected. So you could see spikes in the wind speed, but the wind direction didn't change at all. And also the opposite. And we've also seen it both ways, so that the wind speed increased, or also where the wind speed decreased slightly.
Okay, thanks.
Other questions? If not, I have a very simple question. Should we move the wind sensor farther away or closer?
Yeah, that's a good question, but a difficult one. I guess you'd have to run simulations in order to determine a better position. But then there's also always the danger of generating other issues that you might not have expected before. So relocating the sensor is a difficult topic, and I think also the responsibles at Zurich Airport want to avoid having to reposition it.
I see. Good. Any other questions? If not, thank you very much, Jan, for the nice presentation.